This is millions of tons of concrete holding back the Colorado River. But before engineers could build any of it, they faced a surprisingly simple problem.
You can't excavate a foundation, place millions of cubic yards of concrete, and build a 700-foot dam while a powerful river is flowing through your construction site. Crews attacked the canyon from multiple headings: drill holes, load explosives, blast the rock, remove the debris, then move forward and do it again. So engineers proposed something enormous before the dam itself even began, and temporarily send the Colorado River around the construction site. These weren't small pipes. Each tunnel was excavated roughly 56 feet in diameter, large enough to swallow buildings, trucks, and enormous quantities of river water. And the environment was brutal. Summer temperatures outside could exceed 110 degrees, while conditions inside the tunnels could become even hotter. Construction couldn't simply stop when conditions became uncomfortable. The schedule was aggressive, and crews worked around the clock to get the river out of the way. Once excavated, major portions of the tunnels were lined with concrete so they could safely carry the Colorado River around the future dam. Then came the moment everything depended on. Engineers needed to block the natural channel and convince the Colorado River to take the route they had built for it. In November 1932, the river was diverted. The Colorado abandoned its natural path through the construction zone and rushed through the tunnels instead. Now, for the first time, crews could reach the ground underneath the future Hoover Dam. And what they found wasn't ready for concrete.
A structure this massive couldn't simply sit on loose river sediment. Engineers needed the dam founded against competent rock. So crews excavated downward, removing enormous quantities of material, until they reached bedrock capable of supporting the dam. But engineers had another foundation problem, and this one was hundreds of feet above them. Loose rock on the canyon walls could fall directly onto the workers below, so men known as high-scalers were lowered over the cliffs on ropes. They hung hundreds of feet above the river while operating heavy jackhammers, drilling rock and removing unstable material from the canyon face. Falling rock was such a constant threat that workers improvised hardened head protection, an early version of the construction hard hat. Only after the riverbed and canyon walls were prepared could engineers finally begin constructing the structure everyone had come to build. In 1933, concrete placement began. But engineers immediately faced a problem that doesn't exist at ordinary construction. Concrete generates heat as cement hydrates. On a sidewalk, that's manageable. Inside a structure hundreds of feet thick, that heat has nowhere to escape quickly. Engineers estimated that if Hoover Dam were poured as one continuous mass, it could take roughly a century or even longer for the interior to cool naturally. And uneven cooling means uneven contraction. At this scale, uncontrolled temperature differences could produce serious cracking. So engineers didn't build Hoover Dam as one giant pour. They divided it into roughly 215 vertical columns, constructed from individual concrete placements. Concrete arrived in enormous buckets suspended from cableways stretched across the canyon. Layer by layer, block by block, the dam began rising. But dividing the concrete wasn't enough. Engineers wanted to accelerate cooling. So they embedded cooling pipes inside the concrete and circulated chilled water through them, pulling heat out from the interior. In effect, engineers were refrigerating one of the largest concrete structures ever attempted. After the concrete cooled and contracted, grout was injected into the joints, helping transform the individual placements into a unified dam. With the temperature problem controlled, Hoover Dam rose rapidly from the canyon floor. The shape wasn't arbitrary. Hoover Dam is enormously thick near its base, roughly 660 feet, but only about 45 feet thick near the top. That's because water pressure increases with depth. The lower portions of the dam must resist far greater forces than the top.
But mass isn't the only thing keeping Hoover Dam standing. Look at it from above, and another engineering strategy becomes obvious. Hoover is an arch gravity dam. Its enormous weight resists the water, while its curved geometry helps transfer part of the load into the canyon walls.
Gravity pushes the structure into its foundation. Arch action distributes force toward the canyon. Two structural principles working together.
Once the dam could hold water, engineers began changing the river again. The Colorado River began backing up behind the dam, creating Lake Mead, one of the largest reservoirs ever created in the United States. The reservoir transformed miles of desert canyon into stored water that could be controlled instead of simply rushing downstream. But Hoover Dam wasn't built merely to stop water. Engineers designed a pathway through the mountain that could turn falling water into electricity. Water enters the intake towers and travels through massive pipes called penstocks toward turbines far below. As the water drops, gravitational potential energy becomes motion. That moving water spins enormous turbines. The turbine rotates a generator, converting mechanical energy into electrical energy that can be transmitted hundreds of miles away. The same water that enters from Lake Mead eventually returns to the Colorado River downstream. Hoover doesn't consume the water to generate electricity. It extracts energy from its controlled descent. At full capability, Hoover's power plant can generate more than 2,000 megawatts of electricity.
Engineers also needed a backup plan for water the turbines couldn't handle. Enormous spillways were constructed to safely route excess reservoir water around the dam.
All of this happened during the Great Depression. Thousands came looking for work, and an entire community, Boulder City, was developed to support the project. Tunnel crews, surveyors, equipment operators, concrete workers, and high-scalers worked under conditions that would be almost unimaginable on a modern construction site. There's also an eerie coincidence in the project's history. Surveyor J.G. Tierney drowned while investigating the dam site in 1922. 13 years later, Despite the scale, heat, tunneling, excavation, and danger, construction moved remarkably fast. Hoover Dam was completed in 19 massive project finished ahead of its original schedule. The finished dam rises more than 726 feet above its foundation and stretches more than 1,200 feet across Black Canyon. And this is why calling Hoover Dam a giant concrete wall misses most of the engineering. The wall is only one part of an enormous hydraulic, structural, and electrical system. To build it, engineers had to solve the problems in exactly the right order. Expose the foundation, stabilize the canyon, control concrete temperature, build the dam, store the water, then put that water to work. Nearly a century later, every part of Hoover Dam still tells the story of a problem engineers had to solve: geology, construction logistics, and power generation. Hoover Dam wasn't built by pouring concrete. Engineers first moved the Colorado through mountains, used gravity in enormous reservoirs, and then turned that stored water into electricity.